Hello and welcome. In this video, we'll explore the Dying ReLU problem, its causes and its solutions. In video 16, we observed that ReLU is a simple and efficient activation function that plays a key role in reducing the vanishing gradient problem. However, like any technique, its strengths come with certain limitations. In this video, we will explore one of the major issues associated with ReLU, that is the Dying ReLU problem. To understand Dying ReLU problem, we revisit behavior of ReLU. It is an activation function that outputs the input if it's positive and zero if it's negative. This means that in case of a negative input, output of the neuron becomes zero. Once this occurs, the neuron effectively dies because it stops learning. The gradient is zero and its weights are never updated. So, the phenomenon where neurons stop activating because ReLU converts all negative inputs to zero is known as the Dying ReLU problem. Let's explain this problem with the help of this figure, which illustrates a neural network specifically designed to demonstrate the Dying ReLU problem. The hidden layers of the network consist of 12 neurons, and as shown, 7 of these neurons produce an output of 0. This occurs because the ReLU activation function outputs 0 for any negative input. When a neuron consistently receives negative inputs during training, it becomes inactive, meaning it stops firing and no longer contributes to the network's learning process. In this figure, the high number of inactive neurons highlights how ReLU can lead to neuron death, ultimately limiting the model's learning capacity and effectiveness if not properly addressed. This results in sparse activation, where only a few neurons are active at a time, in contrast to dense activation, where most neurons contribute to the output. Now let's examine the causes of the Dying ReLU problem. There are 3 major causes: weight initialization, large negative biases, and high learning rate. We will begin with the first one, weight initialization. If weights are set in a way that makes ReLU neurons mostly output negative values, which ReLU turns to 0, those neurons can become permanently inactive. Here, we describe a simple example of the Dying ReLU problem caused by improper weight initialization, specifically using a negative weight. In this case, the weight W equals -0.5, the input X equals 2, and the bias is ignored for simplicity. The pre-activation value Z, which is also called as weighted input, is calculated using this equation. It outputs -1. When the ReLU activation function is applied, it outputs 0. Since the output is 0, this neuron effectively becomes inactive for this input. If such negative pre-activations persist across inputs due to poor initialization, for example, weights are too negative or too large in magnitude, the neuron may never activate, hence dying, contributing nothing to the learning process. A large negative bias term in the neuron can cause its output to consistently fall below 0. Now we demonstrate how a large negative bias can contribute to the Dying ReLU problem, even when the weight is positive. In this case, the weight W equals 0.3, the input X equals 1, and the bias B equals -1. The pre-activation value is calculated using this equation. It outputs -0.7. When this is passed through the ReLU activation function, the output becomes 0. Despite having a valid input and a positive weight, the large negative bias shifts the activation below 0, leading the neuron to output 0. If such biases persist across many neurons and inputs, they can suppress activations entirely, causing those neurons to become permanently inactive, hence, dying. High learning rates can lead to weights that are too negative, causing the neuron to consistently output 0. Here we illustrate how a high learning rate can lead to the Dying ReLU problem during backward pass. These are the assumed values. Weight W is 0.5 and input X is 2 and learning rate is 1. We skip forward pass calculations and show computations performed during the backward pass to highlight the impact of learning rate on the Dying ReLU problem. Assume gradient of the loss with respect to the weight W is 10. Using a high learning rate, the updated weight named as W new becomes -9. When input x equals 2 is provided, the pre-activation value becomes -19, and applying the ReLU activation yields 0. This drastic weight update caused by the high learning rate has pushed the neuron's activation into a deeply negative region, making the ReLU output 0. If such extreme updates persist across training, they can render neurons permanently inactive, illustrating how aggressive learning rates can kill ReLU neurons, severely impairing the network's ability to learn. To mitigate the dying ReLU problem, several strategies can be employed during model design and training. One effective approach is using leaky ReLU, a variation of ReLU that allows a small, non-zero gradient for negative input values, ensuring that neurons maintain some level of activity even when the input is negative. Additionally, exploring alternative activation functions such as exponential linear unit or parametric ReLU can also help reduce the chances of neuron inactivation. Another important factor is the learning rate. Using a lower learning rate can prevent weights from becoming excessively negative during updates, which in turn reduces the risk of neurons outputting 0 permanently. Lastly, employing proper initialization techniques for weights and biases can ensure that neurons start with values more likely to keep them active during the early stages of training, improving overall learning dynamic. That wraps up today's video. Please don't forget to subscribe our channel, like the video, share, and comment it to stay updated with this series.